Welcome, everyone. Thank you for joining me today. I'm excited to present to you the question series with answers and explanations specifically tailored for civil engineering exams. Today, we'll focus on the strength of materials. Over the course of this session, we'll go through various questions, explore their answers, and discuss the key concepts behind them. So let's get started and make this a productive and insightful experience for everyone. Let's talk about stress. So the key formula here is stress equals force divided by area. Essentially, stress measures how much internal resisting force is generated within a material when an external load is applied. It's like imagining pushing on a surface. How that force is distributed over the area really matters. The bigger the force and the smaller the area, the higher the stress. This concept is crucial because it helps us understand how materials behave under different loads. When we talk about stress, we're focusing on the internal forces that develop to resist those external forces, which is fundamental in analyzing the strength and durability of materials in engineering. The answer to this question is N per square millimeter or Pascal. Now, let's understand why that is. Stress is essentially the force applied over a specific area. So, when you think about the units, force is measured in newtons, and area is measured in square meters. Therefore, the unit of stress becomes newtons per square meter, which we call Pascal. This connection is important because it helps us quantify how much force is being applied relative to the area, which is fundamental in material science and engineering. Recognizing that stress is force divided by area really ties the concept together, making the units logical and consistent with how we measure physical quantities. So, when we talk about strain, we're referring to the change in length divided by the original length. Basically, it's a way to measure how much an object deforms relative to its initial size. An important point here is that strain is asterisk dimensionless, meaning it doesn't have any units attached to it. Think of it as a ratio, how much something stretches or compresses compared to its original size. This concept is crucial because it helps us understand how materials respond to forces without getting bogged down by units. It's a fundamental idea that ties into the larger theme of material deformation and stress analysis. Let's take a closer look at what Young's modulus represents. The answer here is stress divided by strain. Essentially, it measures how stiff a material is within its elastic limit. When a material is deformed under a load, stress is the force applied per unit area, and strain is the relative deformation or extension. Young's modulus tells us how much stress is needed to produce a certain amount of strain, giving us a clear picture of the material's stiffness. The higher the Young's modulus, the stiffer the material. This concept is fundamental because it helps us understand how materials respond to forces and how they can be used in real-world applications. Remember, it's all about understanding the material's behavior within elastic limits, ensuring it returns to its original shape after the load is removed. All right, let's take a closer look at this important relationship. When we talk about stress and strain within the elastic limit, stress is directly proportional to strain. What does that mean? Essentially, if you increase the stress applied to a material, the strain or the deformation increases proportionally, as long as we're within that elastic limit. This linear relationship is the foundation of Hooke's law. So, in simple terms, Hooke's law states that the force needed to stretch or compress a material is directly proportional to the displacement or deformation, up to a certain point. Remember, this proportionality only holds true within the elastic limit, beyond which the material may undergo permanent deformation. So, understanding this proportionality helps us predict how materials respond to forces, which is fundamental in designing safe and reliable structures and components. Let's take a closer look at how axial load affects a material's dimensions, specifically in the lateral and longitudinal directions. When a material is stretched or compressed, it doesn't just change length, it also changes in width or thickness. The answer to this behavior is called lateral strain or longitudinal strain, depending on the direction we're focusing on. What's interesting here is that the material's response in the lateral direction, its width or diameter, can tell us a lot about its internal properties. This effect, caused by the axial load, is fundamental to understanding material behavior under stress. Now, moving on to Poisson's ratio. This is a key concept in material science. It essentially quantifies how much a material becomes thinner or thicker in the lateral direction when it is stretched or compressed longitudinally. Think of it as a ratio that links the axial deformation to the lateral deformation. Understanding Poisson's ratio helps us predict how materials will behave under various load conditions, which is crucial in designing structures and components that are both strong and reliable. So, in essence, by examining how a material responds laterally when subjected to axial loads, and knowing Poisson's ratio, we gain important insights into the material's overall elastic behavior. This fits into our broader goal of understanding material mechanics and ensuring safety and durability in engineering applications. The answer here is the 45-degree plane. Now, why is that? Well, shear stress reaches its maximum at an angle of 45 degrees to the principal plane. This is a fundamental concept in understanding how shear stresses behave within a material under load. When analyzing stress, it's crucial to identify the plane where shear stress is at its peak, because that's often where failure can initiate. So, in this case, the maximum shear stress occurs precisely on the plane inclined at 45 degrees. Recognizing this helps us better predict material behavior and design safer, more reliable structures. The answer here is that the maximum stress a material can withstand without undergoing permanent deformation is known as its elastic limit. Now, let's delve a bit deeper into what that really means. When a material is stressed within this elastic limit, it can return to its original shape once the load is removed. This is the key point. It's all about the material's ability to recover after being deformed. However, beyond this elastic limit, things change. If the stress exceeds this point, the material enters what's called the plastic range. Here, it no longer fully recovers its original shape, and permanent deformation occurs. This is important because it marks the boundary between elastic behavior and plastic behavior in materials. Connecting this to our overall theme, understanding the elastic limit helps us predict how materials will behave under different loads and ensures we don't unintentionally cause permanent damage. It's a fundamental concept in material science that guides us in designing safe and durable structures. Now, let's look at how we calculate the bending stress, which is represented by the symbol sigma. In this context, sigma equals my over I here. My stands for the bending moment at the specific point we're examining, and I is the moment of inertia of the cross-section. This formula is essential because it helps us understand how much stress is induced in a beam when it's subjected to bending. Remember, the greater the bending moment, the higher the stress, and the moment of inertia tells us about the stiffness of the cross-section. Larger I means less stress for the same bending moment. So, this formula is a key tool in our structural analysis, allowing us to predict where and how much a beam will bend and stretch under load. And speaking of the formula, it's central to our understanding of bending stress, which brings us to our next question. What is the actual formula for bending stress? Now, let's look at the answer to this question: ultimate stress or working stress. Essentially, this is the stress that a structure experiences under normal loading conditions. It's important because it helps us ensure the safety of the structure during its regular use. The explanation here is that ultimate or working stress is what keeps the structure safe under load. It's the stress level that the material or structure can handle without failing during everyday use. Moving on to the next point, the question is, what is the factor of safety? This is a critical concept in structural design. The factor of safety is essentially a safety margin the engineer applies to account for uncertainties, like material imperfections, unexpected loads, or future deterioration. In simple terms, it's a number we multiply the actual or expected load by to make sure the structure remains safe, even if conditions are not exactly as predicted. Connecting this back to our overall theme, understanding these concepts helps us design structures that are not only functional, but also reliable and safe over their lifespan. It's about balancing efficiency with safety, ensuring that structures serve their purpose without risking failure.